Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the paper Memento, Fine-Tuning LLM Agents Without Fine-Tuning LLMs. Are you ready to explore how this work is changing the landscape of large language model agents?
Absolutely. This paper introduces a new learning paradigm for LLM agents, allowing them to adapt continually without the need for expensive fine-tuning of the underlying models. That's a big deal, isn't it?
It really is. Traditionally, LLM agents either rely on static, handcrafted workflows or require computationally intensive gradient updates to their parameters. But Memento proposes a memory-based online reinforcement learning approach. Can you explain what that means?
Sure. Instead of updating the LLM's parameters, Memento uses an external memory to store past experiences. The agent then retrieves relevant cases from this memory to guide its decisions. This is formalized as a memory-augmented Markov Decision Process, or MMDP.
That's right. The MMDP introduces a memory space into the standard MDP framework, allowing the agent to learn from its own history. The agent's policy is continually updated based on environmental feedback, but the LLM itself remains frozen. Isn't that similar to how humans learn?
Exactly. The authors draw inspiration from human memory mechanisms. Humans encode experiences as episodic traces, distill them into abstract rules, reinforce them through feedback, and retrieve them when facing similar problems. Memento mimics this by storing and retrieving cases in its memory.
Let's talk about the architecture. Memento is implemented as a planner executor framework. The planner is an LLM-based, case-based reasoning agent, and the executor is another LLM that interacts with external tools. How does this two-stage process work?
The planner receives a task, queries the case memory for relevant past experiences, and generates a plan. The executor then carries out each subtask, using tools as needed. After each iteration, the planner assesses progress and replans if necessary. Once the task is complete, new experiences are written to the case memory.
That's a clever design. The memory itself can be non-parametric, where cases are simply appended and retrieved by similarity, or parametric, where a queue function is learned to guide retrieval. What's the advantage of each approach?
Non-parametric memory is simple and efficient, relying on similarity search. Parametric memory, on the other hand, learns to assign utility to cases, allowing for more adaptive and selective retrieval. Both approaches have their strengths, and Memento supports both.
The paper evaluates Memento on several benchmarks, including GAIA for long-horizon tool use, DeepResearcher for real-time web research, SimpleQA for factual precision, and HLE for academic reasoning. How did Memento perform?
Memento achieved top 1 performance on the GAIA validation set, with 87.88% pass-3 and 79.40% on the test set. On DeepResearcher, it reached 66.6% F1 and 80.4% PM, outperforming state-of-the-art training-based methods. Case-based memory added 4.7% to 9.6% absolute points on out-of-distribution tasks.
That's impressive. It shows that memory-based continual learning can rival or even surpass traditional fine-tuning approaches, especially in open-ended, real-world scenarios. Let's dig deeper into the methodology. Can you walk us through the MMDP formulation?
Of course. In the MMDP, the agent maintains a case bank, which is its memory. At each time step, the agent retrieves a case based on the current state, reuses and adapts it via the LLM, takes an action, receives a reward, and observes the next state. The new experience is then added to the memory.
The retrieval policy is key here. It's learned using soft queue learning, which encourages diversity in the cases retrieved. The queue function estimates the value of selecting a particular case, and the retrieval policy is a softmax over these queue values. Isn't that right?
Yes, that's correct. The queue function can be learned from scratch via temporal difference learning, or approximated using a kernel-based method that leverages state similarity. This allows the agent to generalize from past experiences to new situations.
The implementation in deep research scenarios is particularly interesting. Memento alternates between case-based planning and tool-based execution, integrating three memory modules: case memory, subtask memory, and tool memory. How do these modules interact?
The case memory stores high-level planning experiences, the subtask memory tracks active subtasks and their results, and the tool memory logs tool interactions. The planner uses the case memory to inform its plans, while the executor uses the tool memory to decide which tools to invoke.
The memory management is also worth noting. In the non-parametric setting, cases are retrieved by similarity, while in the parametric setting, the queue function guides retrieval. The reward signal is binary, and the queue function is trained as a binary classifier. Why is this important?
Using a binary classification loss provides more stable training signals, especially when rewards are sparse. It also allows the agent to learn which cases are most useful for planning, improving the quality of retrieved experiences over time.
Let's discuss the tool usage. Memento supports a wide range of tools, including search engines, web crawlers, document processors, and code execution environments. This enables the agent to handle complex, multimodal tasks. How does this compare to previous approaches?
Previous agents often relied on a fixed set of tools or required retraining to add new capabilities. Memento's modular design and unified protocol allow it to flexibly integrate new tools and adapt to diverse tasks without retraining the LLM.
The experiments section is packed with results. On the DeepResearcher dataset, Memento nearly doubled the F1 score of the COT+ RAG baseline. On SimpleQA, it achieved 95.0% accuracy, outperforming all baselines. What does this tell us about the effectiveness of memory-based learning?
It shows that memory-based learning can provide strong factual reliability and mitigate hallucination, especially in single-hop queries. The continual accumulation of experiences allows the agent to improve over time, even in challenging, open-domain settings.
The ablation studies are also revealing. Increasing the number of retrieved cases improves performance up to a point, but too many cases can introduce noise. Planning and tool orchestration systematically improve execution, and case-based reasoning provides consistent, additive gains. What's your take on these findings?
It highlights the importance of careful memory curation and case selection. A small, high-quality memory is more effective than a large, noisy one. Explicit planning and tool use are crucial for complex tasks, and case-based reasoning enhances generalization and continual learning.
The continual learning curves show that Memento's performance improves with each iteration as more cases are accumulated. However, the gains plateau after a few iterations, suggesting rapid convergence. Why do you think that is?
In the simulated environment, the number of unique cases is limited, so the case bank saturates quickly. Once most scenarios have been encountered, additional iterations yield diminishing returns. This suggests that memory-based approaches are especially effective in environments with recurring patterns.
The generalization experiments are also noteworthy. Memento achieved substantial improvements on out-of-distribution datasets, with gains of 4.7% to 9.6%. This demonstrates the power of case-based reasoning in transferring knowledge to new tasks. Would you agree?
Absolutely. By leveraging analogies from past experiences, the agent can tackle novel problems more effectively. This aligns with psychological theories of human problem-solving, where analogical reasoning plays a central role.
The discussion section analyzes tool usage and system efficiency. As task difficulty increases, the number of tool calls rises, but the most challenging problems require more internal reasoning and evidence aggregation. What does this imply for future agent design?
It suggests that effective integration of planning, memory, and evidence aggregation is essential for solving open-ended, long-horizon tasks. Simply adding more tools isn't enough. The agent must be able to synthesize information and adapt its strategy dynamically.
The impact of fast and slow thinking planners is also explored. The fast, non-deliberative planner outperformed the more deliberative one, highlighting the benefits of concise and structured planning. Why might this be the case?
Overly deliberative planning can introduce unnecessary context and redundancy, confusing the executor. Concise planning leads to more effective execution, especially in modular systems where specialization is key.
In conclusion, Memento offers a scalable and efficient pathway for developing generalist LLM agents capable of continuous real-time learning without gradient updates. The combination of memory-based MDP, planner-executor architecture, and case-based reasoning sets a new standard for adaptive agents. Would you like to summarize the key takeaways?
Certainly, Memento enables LLM agents to learn continually from experience without fine-tuning model weights, leveraging memory-based reasoning to guide decision-making. It achieves state-of-the-art performance across multiple benchmarks, demonstrates strong generalization, and provides a principled framework for continual adaptation in deep research scenarios.
That's a great summary. This paper marks a significant step forward in the development of adaptive, memory-augmented LLM agents. Thank you for joining us on this deep dive review. We hope you found it informative and inspiring.
Thank you, everyone. Stay tuned for our next episode, where we'll continue exploring the latest advances in AI research. Until then, keep learning and stay curious.